A Chinese spacecraft is sitting on the far side of the moon. It has never seen Earth. It can't. The moon's own bulk is in the way. Its drill is boring into soil that no mission has ever touched. A robotic arm scoops the loose surface material on top, filling a sealed container with nearly 2 kilograms of rock and dust from the oldest, deepest impact crater in the solar system. Then the ascent stage fires, lifts off from the lunar surface, climbs into orbit, docks with a waiting spacecraft, transfers the container, and begins the journey home. All of it autonomous, all of it executed on the side of the moon that faces permanently away from Earth, relayed through a satellite China launched specifically to make this possible. That was June 2024, and no other nation has done anything close to it. The moon has two faces. The near side is relatively flat, covered in ancient volcanic plains called Maria, dark, smooth regions, formed by lava flows billions of years ago. The far side is completely different, rugged, heavily cratered. The crust is thicker, and volcanic activity was far rarer. Planetary scientists call this the lunar dichotomy, and it's one of the oldest unsolved puzzles in planetary science. Why are two hemispheres of the same object so fundamentally different from each other? The answer is locked in farside rocks. Rocks that, until Chang'e 6, no mission had ever retrieved. Chang'e 6 landed in the Apollo crater, a 500-kilometer-wide basin sitting inside the South Pole Aitken Basin, the largest confirmed impact structure in the entire solar system, roughly 2,500 kilometers across and 8 kilometers deep. It formed 4.25 billion years ago, during the era of heavy bombardment, when the inner solar system was being pelted by debris left over from planetary formation. The original impact was so violent, it may have punched through the lunar crust entirely, excavating material from the mantle beneath. That's what made the site scientifically irreplaceable. These weren't just surface samples. They were potentially mantle material from layers of the moon no mission had ever directly reached. Getting there required solving a problem that had stopped every other nation from even trying. The far side has no line of sight to Earth. No direct radio contact is possible. You can't command a spacecraft you can't talk to. China's solution was a relay satellite launched 2 months before Chang'e 6, placed in a high elliptical orbit where it could see both the lunar far side and Earth simultaneously. A communications bridge, purpose-built for this one mission, across 250,000 miles of space. The samples came back. Chinese scientists analyzed them. 4 papers were published in the journal Nature in 2025 from teams at China's Institute of Geology and Geophysics, the National Astronomical Observatories of the Chinese Academy of Sciences, and Nanjing University. What they found was significant. The far side's mantle is substantially more depleted in water than the near side's. The leading interpretation is that the original South Pole Aitken impact was so energetic, it melted and displaced the water-bearing minerals, permanently altering the far side's composition, all the way down to its roots. That's a direct answer to the dichotomy question. The two hemispheres aren't just shaped differently on the surface, they're different in their deep interior, and a 4-billion-year-old collision is likely why. The samples also yielded the first direct measurements of the moon's ancient magnetic field from the far side. That data showed a possible rebound in field intensity around 2.8 billion years ago. Evidence that the moon's internal dynamo didn't simply fade out steadily, it flickered. That's a window into the thermal history of a world that went cold, long before Earth's oceans finished forming. And the age of the South Pole Aitken Basin itself was pinned down more precisely than ever before. 4.25 billion years, giving planetary science a sharper anchor for understanding the timing of large impacts across the entire inner solar system. This wasn't Chang'e's first major discovery. In 2020, Chang'e 5 returned samples from the near side and found evidence of volcanic activity as recently as 2 billion years ago. A full billion years later than scientists had thought, the moon went geologically quiet. The moon was supposed to be cold and dead by 3 billion years ago. Chang'e 5 proved otherwise. James Head, a planetary scientist at Brown University who trained Apollo astronauts in the 1960s and has since collaborated with Chinese researchers, described their sample analysis facility in Beijing as first class. The program has a cumulative logic to it: orbital mapping, soft landing, roving, sample return from the near side, sample return from the far side. Each mission built the capability base for the next. None of them were dead ends. And now, that sequence is pointing somewhere specific. China's Chang'e 7 launches in the second half of 2026. Its target, the lunar South Pole. Specifically, the illuminated rim of Shackleton Crater, near 82 degrees south latitude. The reason is water. The permanently shadowed craters at the lunar South Pole are among the coldest places in the solar system. Some haven't received direct sunlight in over 1 billion years. Temperatures inside fall to around -240 degrees Celsius, colder than anywhere on Earth's surface by a vast margin. Water ice delivered by ancient comets and asteroids can't sublimitate at those temperatures. It just stays, locked in the soil, preserved across geological timescales. Multiple orbital missions, including NASA's Lunar Reconnaissance Orbiter and India's Chandrayaan-1, have provided strong indirect evidence that water ice is there, but no mission has ever gone down into one of those craters and directly sampled it. Chang'e 7 will try. The mission includes 5 separate spacecraft: an orbiter, a lander, a rover, a relay satellite already in orbit, and something entirely new, a hopping probe. The hopper uses rocket propulsion to make flights of at least 10 kilometers at a time, targeting landings inside permanently shadowed craters that no wheeled rover can reach. After landing, it walks away from its own touchdown point to avoid contaminating the sample site, drills into the regolith, and runs the material through a water molecule analyzer and mass spectrometer. It's looking for water ice, methane, and other frozen volatiles directly. For the first time in the history of lunar exploration, if it finds confirmed water ice, the implications are immediate and practical. Water can be electrolyzed into hydrogen and oxygen, rocket propellant. It supports life. A confirmed water deposit at the South Pole doesn't just make a moon base scientifically interesting. It makes one physically viable in a way it simply isn't without it, because the alternative is shipping every drop of water from Earth at enormous cost and complexity. Chang'e 8 follows in 2028 and goes a step further, testing the actual use of lunar resources on-site. 3-dimensional printing with lunar regolith, sealed ecosystem experiments, the explicit goal to demonstrate self-sufficiency, to show that a permanent human presence on the moon can be maintained without relying on constant resupply from Earth. Together, Chang'e 7 and 8 form the foundation for the International Lunar Research Station, a permanent South Pole outpost China is targeting for the early 2030s, with 12 nations already signed on as partners. There is a substance embedded in the lunar regolith called helium-3. The solar wind has been depositing it into the moon's surface for billions of years, working it into the top few meters of soil across the entire lunar surface. Scientists estimate total lunar reserves of between 1 million and 5 million tons. On Earth, helium-3 exists only in trace quantities. It's extraordinarily difficult to produce or collect in any meaningful amount. On the moon, it's simply there, waiting. Ilium. 3 is a candidate fuel for a specific type of nuclear fusion reaction, one that produces dramatically less radioactive waste than conventional fusion approaches. No one has built a working helium-3 fusion reactor. The engineering remains unsolved, and most researchers put large-scale extraction in the category of possibilities measured in decades, contingent on fusion technology that doesn't yet exist. It's a long game, not an imminent one, but here's the detail that sticks. China's very first lunar mission, Chang'e 1, launched in 2007, carried instruments specifically designed to map the distribution of helium-3 across the lunar surface. That was before China had soft-landed anything on the moon. Before rovers, before sample returns. Before any of it, the resource mapping was built into the original scientific agenda from the very beginning of the program. The pattern across nearly 20 years is consistent. Map the resources, move toward utilization. Whether helium-3 ever becomes a practical energy source depends on physics and engineering problems that remain open. What isn't open is the question of whether China has been thinking about the moon as more than a destination to visit.